So this is the first of two lectures on chapter 8, which is about first order RC or RL circuits. So let's begin by studying this simple but not the most simple circuit in some detail. So we have a voltage source, a resistor, a capacitor. There is a switch and another resistor, and the switch is open for t less than 0, and the switch is closed at t equal to 0, and we are asked to find the capacitor voltage and the capacitor current for all times. We are also told that the switch was open for a very long time. Usually this is always given, and what that means is that for t less than 0, the circuit had reached some DC steady state, because whenever switches are opened or closed, capacitor voltage is changed with time. So we are assuming that for t less than 0, whatever changes had to occur had finished occurring, and the capacitor had in fact a DC state, and therefore no current was flowing in the capacitor for t less than 0, because as you know, in DC conditions, capacitor does not carry any current. Alright, so with that, we follow the steps for analyzing this circuit. So the question is find VC and IC for all time. So we start with t less than 0. Step 1 is we draw and solve the circuit for t less than 0. So this is our original circuit. For t less than 0, the switch is open. For t less than 0, the capacitor is an open circuit because it does not carry any current, as we just said. So this is our circuit, and so there is no current flowing anywhere because there is no closed path, and the capacitor voltage, therefore, so there is no current in R1, and therefore the capacitor voltage will be equal to V1, the voltage source voltage, right? And the capacitor current, of course, is 0. So these are the conditions for t less than 0. Then step 2 is we draw and solve the circuit at t equal to 0 plus. 0 plus is the moment when the switch is closed. So just when the switch is closed, what happens? What are the voltages and currents just after the switch is closed? So that is step 2. So this is the circuit drawn. Now a capacitor, as we saw last time, the capacitor voltage does not change instantaneously when the switch is closed. So whatever voltage the capacitor had before the switch closed, it will retain that voltage right after the switch is closed. So we can say that the capacitor voltage in this circuit is V1 at the moment of the switch closing. So this circuit is drawn at this moment, only in this moment of time, all right? And at that moment of time, the capacitor voltage is V1, and therefore it is often convenient to draw the capacitor as a voltage source so that we can solve the circuit. We could draw a capacitor and write the voltage, but because we know the voltage at this moment in time, we usually draw a voltage source. Okay, so with this voltage source, one more important point. So the capacitor voltage does not change when the switch is closed, but all other voltages and currents will change in the circuit. Well, not all. I mean, the voltage source voltage is not going to change, but everything else basically will change. So the capacitor current specifically, which is what we are asked to find, will change. So we solve this circuit to find the current IC. So this is a peculiar but very simple circuit. So this voltage is V1, this voltage is V1. Therefore there is no current in R1 because the voltages on both sides of R1 are the same. This voltage is V1, so there is a current flowing in R2, and that R2 current is flowing in the clockwise direction, and that current is V1 by R2. And that direction is opposite to IC, so IC is minus V1 by R2. So IC was 0 for t less than 0. It became suddenly at t equal to 0 plus minus V1 by R2. Alright, so that is at t equal to 0 plus. And then of course step 3 is we solve the circuit for t greater than 0. So this is the circuit for t greater than 0, and now this is of course a main part of the solution of such circuits. So we have to solve this circuit. And to solve this, so again we look at this, I have defined this as ground. This node, two nodes, one node voltage is known, it is V1. So we have only one unknown voltage Vc. So we write a KCL at Vc. So we'll say Vc minus V1 by R1, which is this current, plus Vc by R2, which is this current, plus Ic equal to 0. So that becomes our KCL. Now this has of course two unknowns, Vc and Ic, but we know Ic in terms of Vc because of the IV characteristics of the capacitor. So we say Ic is C dV dt. So we substitute for Ic here and we get one equation in Vc. So I have written it here, Vc by R1, Vc by R2, Ic dV dt, and V1 by R1 goes to the right hand side because V1 is a known quantity. And then defining this 1 by R1 plus 1 by R2 as some equivalent resistance Req, and then we can write this equation as dVc by dt plus Vc by, this is Req times C, equal to V1 by R1C. Alright, so this is the equation for Vc and we have to solve this equation. This is a first order differential equation with constant coefficients. When the coefficients of the derivative and the Vc term are constant, it is called a differential equation with constant coefficients. When the right hand side is not 0, this equation is called a non-homogeneous equation, and the order of the equation is determined by the order of the derivative. So this has only a first derivative, so this is called a first order equation. So whenever there is, well, we'll come to this, but one energy storage element in a circuit, one C or one R, the equation that we'll end up with will be a first order equation. If there are two energy storage elements, two C's or two L's, or one L, one C, then it will be a second order differential equation, which we will solve in chapter 9, which is the next chapter. Alright, so now we have to solve this equation. I think you have solved such equations before, first order equations. Also, you are doing the solution of differential equations in the maths course in parallel. So I am not going to go through the derivation. The derivation is here. So I have the derivation. There are many ways of solving this. Here is one way. So you take the Vc by Req on the other side, and then you kind of do separation of variables. So you bring everything with Vc on one side, dt on the other side. You integrate. In order to integrate, you substitute this with x, and then etc, etc, and then etc, etc, and you will get where is the equation? So Vc as something where x0 is the integration constant. So t0 becomes k0 becomes x0. x0 is the integration constant. And then, so let's pick it up from here. So Vc of t is equal to tau. So tau is what? Tau is R equivalent C. The tau is a time constant. I'm assuming you are familiar with all this, so I'm rushing through it, kind of. So tau is known, x0 is an integration constant, e raised to minus t by tau plus Req by R1 V1. To find x0, we use what is called as an initial condition, which is what was the value of Vc at t equal to 0 plus. 0 plus, okay, always remember 0 plus. For Vc it's okay, 0 plus or 0 minus is the same. But when we do for Ic at 0 plus is different from Ic at t less than 0, and we must use the value after the switch is closed because that is the circuit we are solving. Alright, so we already know that the capacitor voltage at t equal to 0 plus was V1. We already derived that. So we use this knowledge to find x0. So we say this v1 equal to tau and t at t equal to 0, e raised to 0 is 1. So we got all this and we find x0. Alright, and having found x0, we write the final expression for Vc of t. So Vc of t, the capacitor voltage in this circuit for t greater than 0, has this form. It is a constant times e raised to minus t by tau plus another constant, where of course, as we already saw, tau is R equivalent into C. Now notice that in this equation, as t tends to infinity, e raised to minus infinity is 0. I hope you know that. So e raised to minus infinity becoming 0, this terms become 0. So as t tends to infinity, the voltage, capacitor voltage, acquires this DC value, which is called the final value of the capacitor voltage. So this is the final steady state value of the capacitor voltage for this circuit. Alright, which is R2 by R1 plus R2 into V1. Now let's see if that makes sense, right? So at t equal to infinity in this circuit, the capacitor will have acquired a DC voltage and no current will flow in the capacitor. So we can again represent it as an open circuit. So the only current will be flowing will be in this V1, R1, R2 loop. And then this voltage across the capacitor is simply R2 by R1 plus R2 of V1 by voltage division, which is this value. So it makes sense, right? That's kind of a confirmation. So we say this is V final. Now we are asked to find IC also. So IC actually is directly found in this circuit by, well, for any circuit, if the say capacitor current is asked and if you found the capacitor voltage, you just use the capacitor equation. So you say IC is dVc dt. We've already found Vc. So we just differentiate this and put all values and everything, and finally you will get IC of t equal to minus V1 by R2 e raised to minus t by tau. Okay, if you solve all of this, you will get this. Again, this makes sense. So let's look at the value at t equal to 0. So at t equal to 0, the exponential term is 1, and so we get IC equal to minus V1 by R2, which we had already found. So this kind of confirms that we have not made any mistake anywhere. So these are the current voltage and the current. Let us plot these. You must, so in fact, one thing you must learn to do is plot these voltages and currents in such circuits. All right. So I have taken some representative values. So V1 is 5 volts, R1, R2 are 10 and 10, and C is 250 nanofarads. So if we put these values here, R1 is equal to R2, so this will be 0.5 V1. V1 is how much? 10, what did I say? 5. So this will be 2.5 and this will also be 2.5. And V1 is 5 by R2 is, I'm forgetting, 10. So this is 5 by 10, 0.5 amperes. So you'll get 2.5 e raised to minus t by tau plus 2.5 volts. IC is minus 0.5 e raised to minus t by tau. So if we plot Vc at t equal to 0, Vc is 5 volts. We already know that, 2.5 plus 2.5, and it goes to 2.5 volts as t tends to infinity. Alright, and the current starts out at minus 0.5 amperes at t equal to 0, jumps actually. It was 0 for t less than 0, it is jumping to minus 0.5, and the current also eventually goes to 0. Alright. Now let us study this some more. So these are the same equations from before. Now if we write Vc of t, this expression as some constant a times e raised to minus t by tau plus some constant b, then we can see that as t tends to infinity, the Vc is simply b because the first term goes to 0. So we get, as we already saw this. So the final value I've called Vf in this expression is simply the constant term, which is B. The initial value at t equal to 0 plus is, this is e raised to 0 is 1, so this is A plus B. So the initial value in this equation of the for the capacitor is A plus B, and that we call as Vi, I for initial. So from these two, B is Vf, so we can say that A is Vi minus Vf in terms of A, Vi and Vf. So we can write Vc of t as A is Vi minus Vf e raised to minus t by tau plus Vf, B is Vf. Alright. And tau, as we saw, is R equivalent times C. Now I'm going to generalize this again without proof. I'm going to generalize this and make these statements. Alright, we'll not prove these. They can be proved. They are very easy to prove, but we will not prove them. But here is the kind of generalization. So we say in a circuit containing one equivalent energy storage element, a capacitor or inductor, and I will come to equivalent in a couple of minutes. For now, let us say there is one energy storage element, capacitor or inductor. When a sudden change occurs, so either a switch closes or opens, one switch, many switches, if they close or open, or a voltage or a current source, an independent voltage or current source in this circuit, suddenly changes its value. Alright, that can also happen, the voltage or current suddenly changes value. If that happens, then any current or voltage in that circuit can be expressed by this equation. So where X is either a voltage or a current. So any current or voltage as a function of time after this switch has closed or opened, or this voltage or current has suddenly changed, the current, any current or voltage can be written in this form which we saw here. The same form. So X initial minus X final e raised to minus t by tau plus X final. Alright, where Xi is the value of that voltage or current immediately after the change has occurred. So if the change occurs at t equal to 0, then this is the value at t equal to 0 plus. Xf is the final value of X of that circuit if the circuit is allowed to reach that state, and I'll come to this also later. For now, this is simply the final value. And tau is the time constant, which is equal to Req times C for a capacitor, and it is equal to L by Req for an inductor, and we'll see this in the next lecture, where R equivalent is the Thevenin's resistance seen by the capacitor. Alright, so again I'm not proving this, actually all of this can come out of Thevenin's theorem. Okay, so I should actually know, so this is one very critical word missing which I missed. Linear, in any linear circuit, or it is absolutely essential that the circuit be linear, otherwise this doesn't work. So if the circuit is linear, then this is kind of an extension of Thevenin's theorem, and you can think about it and you'll realize that from Thevenin's theorem, everything that is written on this slide can be derived. So we will not prove it just the way we did not prove Thevenin's theorem, but we'll take this for granted. Now the advantage of this whole statement is that given this knowledge, whenever we are given any circuit, any linear circuit containing one L or one C, we do not need to go through all of this derivation at all. All of this derivation, we did it once, we convinced ourselves for one, and then we generalized it. Now whenever we are given a circuit with one L or one C and some sudden change is happening, switch closing, etc., then we can write any current or any voltage in the entire circuit, write it down as this without derivation, and all we need to find are xi, xf and tau, and all these three are found actually by solving DC circuits. Xi we found by solving the circuit at t equal to 0 plus. Xf we can solve by drawing the circuit at t equal to infinity, which will be a DC circuit again. So by solving two DC circuits and finding the Thevenin's resistance of that is the same circuit, we can find the current or voltage, any current and any voltage in the entire circuit. Alright. So some homework problems, you can utilize this property to solve. Okay. Let us look at this slightly differently. So I want to do a little qualitative study, and I am simplifying the circuit. The circuit we solved was not the simplest. This is the simplest possible circuit. So let's just go through it. So in this circuit, the switch is open for a long time, and we are told that Vc for t less than 0 is 0. Alright, we are told, we always have to be told what was the capacitor voltage for t less than 0 if it was nothing was connected to it. Alright, because as we've seen last time, the capacitor can have a charge on it and it will retain that charge forever if it is kept open circuited. So we must be told this information if the capacitor is not connected in the circuit. Alright, so we are told that this is 0 and the switch is closed at t equal to 0, and we are asked to find the capacitor voltage as a function of time. So I am not solving this. In fact, this is the answer. The capacitor voltage as a function of time is V1 into 1 minus e raised to minus t by tau. I am assuming that you've seen this before. In any case, this is in fact very easily derivable from our generalization. So in fact, let us do that quickly. So in this expression at t equal to 0, e raised to 0 is 1, so 1 minus 1 0, so Vc of t is 0. And at t equal to infinity, the final value is V1, and this circuit finally, with the switch closed, the final steady state will be when the capacitor acquires a voltage of 5 volts. So this is what we would expect it to be. Now, so here is the plot of the voltage. It starts out at 0 and it goes to 5 volts as t tends to infinity. Now writing this, okay, so the capacitor current is CV dVc dt, and this can be written as, and how can it be written? Actually, it can be written as V1 minus Vc by R. Okay, I'm sorry, this is R. It should be consistent here. So let us make this R. Alright, so that is actually just Ohm's law kind of written. So the current, the capacitor current is the same as the resistor current flowing clockwise, and the resistor current is this V1, which is 5 volts, minus Vc divided by R. So it's V1 minus Vc by R. So we get C dVc dt equal to V1 minus Vc by R. Okay, so let's just look at this for a minute. Alright, so look at this equation and the circuit. So what we find is that for t greater than 0, as time passes by, the capacitor voltage is increasing because current is flowing in the loop, and as current flows, the capacitor keeps getting charged more and more. And as the capacitor charges, the capacitor voltage increases. Now, as the capacitor voltage increases, the voltage across the resistor decreases, right? And as the voltage across the resistor decreases, the current in the circuit decreases. Alright, that's what this equation is showing. So as Vc increases, this whole quantity decreases, and so Ic decreases. And so that's what we are seeing here. As a function of time, Ic decreases. That's one. The other is Ic decreases also means that dVc dt decreases. The derivative of Vc decreases. Now in this plot, what is dVc dt? From in this plot, dVc dt is a slope of this line, right? This is Vc on the y-axis, time on the x-axis. So this is dVc dt. So the slope of this line is decreasing as a function of time. So that is why you see the slope is highest here and it's kind of bending over, and at any point in time the slope is lower than at any further point in time, right? This is of course a property of systems which have a derivative equal to the minus of that variable. So dVc dt, when it is equal to some constant minus of the Vc, this kind of behavior occurs. The exponential behavior is a result of this functionality. And I assume that you've seen this for radioactive decay in your 11th, 12th, and perhaps for other things also. It is just kind of important to recognize what is happening here. Okay. One more important thing. So we say that the capacitor gets fully charged. So in this circuit, the capacitor acquires 5 volts only as t tends to infinity. So it's important to remember that in the whole wide world, whenever you connect capacitors across DC voltage sources and resistors, the capacitor never ever gets fully charged, because that happens only at t equal to infinity, which is never ever reached. So the capacitor only approximates the final value that it is supposed to acquire, and for all reasonable time, so you say after 5 tau or 10 tau, the capacitor voltage has become close enough to the DC voltage source voltage that you say, well, it is essentially or practically fully charged, but theoretically or mathematically it is never fully charged. All right. This is sometimes this is relevant. Most times in circuits this is not relevant, but it's an important fact to remember. The other very important thing to remember is that the idea of fully charged capacitors exists only in circuits with DC voltage sources. All right. So we have voltage source, resistor. Resistor is always there. Voltage source, resistor, capacitor. Then you talk about a capacitor becoming fully charged, because fully charged means the capacitor acquiring the voltage source voltage. As we saw at the beginning of the last lecture, if there was a current source here, all right, I hope you remember, if you have a current source here, then of course the resistance becomes irrelevant, and the current is charging the capacitor, and the capacitor keeps on charging forever and ever and ever. It is the notion of fully charged does not apply if there is a current source, because the capacitor never reaches steady state. All right, when you have a current source, the capacitor voltage is increasing linearly with time, and any function that increases linearly with time never reaches a final state. If it is exponential in time, then it is approaching some final value, and that is a fully charged state. All right. So just given any circuit with a capacitor, to say that the capacitor will eventually become fully charged is not correct. It is correct only if it is driven by a voltage source and a resistor in series. Okay. Okay, so here are a couple of examples. So we are given this circuit, and we are told that this voltage Vs of t, it's a voltage source, is 0 for t less than 0, and it suddenly becomes some constant value V1 at t equal to 0, and then it stays at that value, and we are asked to find the voltage Vy across this capacitor. Are we? No. No, we are asked to find Vx. Okay, we are asked to find both. So let's find Vx first, all right? So to find Vx, so although, okay, so here is where I am talking about the idea of equivalent capacitance. So although there seem to be 1, 2, 3, 4, 5, 6 capacitors in this circuit, one says that this circuit has equivalently only one capacitor, because all of these can be combined to form one capacitor. And you know how to combine capacitors. I never talked about it because I assumed that you knew. So anyway, let's go through quickly. So 2C series 2C is C. That C in parallel with C is 2C. That's 2C in series with this 2C is C. C in parallel with C in parallel with C. 3C. So looking to the right of this Vx, this whole thing is one capacitance of value 3C. And so we can replace everything by one capacitor from Vx to ground of value 3C, and then we have Vs, R and 3C. And then we know how to solve that circuit very simply. It is V1 into 1 minus e raised to minus t by tau, where tau is R into 3C. Alright, so this is a very simple circuit to solve, but it is illustrating that there may be many capacitances, but if they can be combined into one, then still our this works, because there is one equivalent energy storage element. And as I said, if there were two equivalent energy storage elements, then we'll end up with a second order differential equation, which we will do only in the next chapter. So for example, if there was a resistance here, some other resistance, then there will be two equivalent capacitances. Okay. I'm not going to solve for Vy. You think about it. This is kind of extracurricular. I am not expecting you to learn this for this course, but it is just a very interesting question and a problem you should be able to solve based on everything that we've done till now in the course, but you think about it. All right. Okay, on another example. So here the question is the same. V1 is suddenly changing from 0 to Vs at t equal to 0, and we are asked to find the capacitor voltage as a function of time. So here what we do is we simply replace this whole thing by its Thevenin's equivalent. So it is Vth Rth across AB, and the C stays the same. Because we are asked to find the voltage across the capacitor, we can get rid of we can transform the rest of the circuit into a Thevenin's equivalent. And I'm not solving this, again this is a very simple circuit to solve. So you'll find that Vth is equal to V1 by 6 and Rth is 2/3 of R, and then of course this is a very simple circuit. So we say Vth etc. etc. Okay. The next question I'm asking is, can you find V2 of t? Now you found Vc of t, can you find V2 of t? Okay, think about it. This is actually, I have used the word quickly because it is you see how quickly you can find it. All right. So I'm leaving this as homework. So this you should learn to do. This one I'm not expecting you to learn, but do it just for fun. This I'm expecting you to do. All right. So this is you must do this at home. All right. So this is the end of this lecture. Next lecture we'll talk about inductor circuits, and about something called sequential switching.